Good evening, everyone. So today I'm going to solve this gravitation chapter question number 7.1. So here it is saying that you can shield a charge from electrical forces by putting it inside the hollow conductor. Can you shield a body from the gravitational influence of a nearby matter by putting it inside a hollow sphere or by some other means? See, let us consider uh, there is a electrical field like this. Okay, and there is a charge. This is charge. The force acting or at this charge will be due to electrical field will be in this direction. Now we need to put a shielding. So if I will shield here by metal box, so metallic sphere. So what will happen? What will happen due to electrical field? So most of the electrons will go in this direction. That is, there will be an accumulation of a negative charge because most of the electron due to the electrical field will go this direction and most of the positive charge will come in this direction. So due to this, what will happen? There will be there will be an electric field will be created in this direction like this. So what happens when electric field is being created? See here, earlier the electric field is from outside, that is in a blue color, and due to the shielding, what happens? Opposite electric field is being created. So what will happen? Net electric field inside sphere will be equal to 0. So no field is acting, no electrical force will act. So this is known as shielding of electric. This is known as shielding. Okay, but in question they are asking, can you shield the body of a body from gravitational influence? So let us consider there is a gravitational influence is like this, because there is a big mass. So gravitational influence will be like this, and if any other charges is there like q1 q2, anything may happens. Now if I will shield with the metallic, not metallic here, if I will shield with anything, so what will happen? In the above cases, what happened? Charge got transfer, but here no mass transfer happen. No mass transfer happens. If no mass transfer happens, then there is no possibility. So no, we can't shield to protect shield a body from gravitational influence. Okay. Now here see uh, part B of the question number 7.1. An astronaut inside a small spaceship orbiting around the Earth cannot detect any gravity. If the space station orbiting around the earth has a large size, can we hope to detect the gravity? If this is the earth and this is a small spaceship, so there will be no effect of the gravity, no effect of gravity. But if we use, let us consider this is earth, and if we use large ship like this, so what will happen? The force at will be different at this different places. Okay, because the distance is r, so this will be r plus h. So what will happen? The force will be difference. So due to difference in the force, due to difference in the force, spaceship spaceship can detect gravity. Okay, I hope you have understood now. This is the question number C of us 1C 7.1C. In this, the question is, it is saying that if you compare a gravitational force on the earth due to the sun to the earth due to the moon, you would find that the sun's pull is greater than the moon's pull. Okay, so why this happens? Is it you would find that the sun's pull is greater than the moon's pull. However, the tidal effect of the moon pull is greater than the tidal effect of the sun. Why this happens? Why this happens? See, it is very simple solution. It is as per this. Let us consider, as we know that the size of the sun is very large, so definitely sun's pull is more than the earth's moon's pull. But at the same time, when we talk about the moon, so what happens? Let us consider this is a moon. Okay, and this is a earth. Okay, now see here what happens actually when we talk about this section, and when we talk about this section, so what will happen? Due to the sun pull, there is a force at this point, and there is another force at this point. Okay, the force at this point is greater, and force at this point is smaller, right? So what we can conclude, that there will be a high tide at this place, but there is a chance of a low tide at this place. At the same time, what happens? Average average pull is very high on the earth, by the earth. So what happens? The earth is trying to move forward, and the force due to the moon is very small as compared to this portion. So what we will see that the earth is moving very fast, but the water remaining at this point will remain at the same position. So what will happen? At this point also you will find there is a high tide, and this portion also you will find high tide. So this is the main reason for the high tide, due to the moon, in spite of less pull, gravitational pull. But at the same time, when we talk about the sun is very far away. So as compared to the moon, so sun's pull is overall everywhere, it is approximately same. So there is a no effect on the tide, no effect on the rising of water, on rising of water. Okay, choose the correct alternative from the question. Okay, so in question it is acceleration due to gravity increases or decreases with the increase in the altitude. Altitude means height. Let us consider this is the earth. So with the increase in the height on the earth so what will happen? So if increase in the height will happen, so what will ultimately happen? Gravity will decrease as per this formula. So g will decrease if height will increase. So finally our answer will be decrease. Now again, second question is that acceleration due to gravity increases or decreases with the increase in the depth of the earth to be uh, a sphere of a uniform density. So as we know that when we go in a deeper than the earth, so what will happen? Let us consider. Let us consider uh, if we want to go deeper on the earth. Let us consider this is the earth. So if we want to go deeper to the earth, so what will happen? We have to, as per this, we have only this type of mass. So when we find the formula for the gravity at the depth of d, so we will got the d. If d will increase, so if depth will increase, so ultimately g will decrease. So g will decrease if depth will decrease, sorry, depth will increase. So our answer will be up, it will be decrease. Now in question number C, acceleration due to gravity is independent of the mass of the earth or the mass of the body. Definitely it is independent of the mass of the body, because acceleration due to gravity has the formula, acceleration due to gravity has the formula small g is equal to capital G m by r square. So that is radius of the earth. So there is no mention, so it will be independent of the mass of the body, not a mass of the earth, because we are including mass of the earth. Okay, so here our answer will be mass of the body only. Now let us discuss about the d's. D, it is written that D, it is written, let us clear all the image. Now see, in section D, it is written that the formula for minus gm minus g into capital M small m 1 by r2 minus 1 by r1 is more or less accurate than the formula for mg r2 minus r1 for the difference in a potential energy between 2 points. So let us consider, if we want to find the potential difference in a potential energy, so we have to use this formula only. This is the formula. Okay, now let us consider gm into small m into, it will be r1 minus r2 by r1 and r2. If we consider this is the earth and this is the radius of the earth as a r1, and this ball or this object has a radius r2. So if we want to find the potential difference, so we have to use this formula. So if we put here gm into small m by r1 r2 into r2 minus r1, so finally we know that this is if we consider that r1, that is the radius of the earth, is very much greater than the radius, this radius, that is r2, then we can replace r1 as and r2 as like this. So r1 and r2, now see here r1 and r2, so this is the r2 distance. So if this is at nearby earth surface, so what will happen, r1 is approximately is equal to r2, so we can put here r1 and r1 is equal to r2. Finally we will get this formula as z capital M by r radius of the earth whole square, because we have considered this approximately is equal to radius of the earth only, into r2 minus r1. So this is your m. So finally we can write this as a small g, that is the acceleration due to gravity, has a formula gm by radius of the earth whole square. So if we put here and this will be mg into r2 minus r1, which is the derived one. So it is the accurate formula, but it has, this formula has been derived. So from a question it is given that which formula is more accurate. Definitely this formula is more accurate. So this is more accurate than the formula mg r2 minus r1. I hope you have understood now. Let us suppose here there existed a planet that went around the sun twice as fast as the earth. Let us consider we have a earth and a sun. So let us consider this is a sun and this is a earth or vital of the earth. So this is your earth, okay, and there is another planet. There is another planet moving in mid between this, such that the time period is half of the time period of the earth. Okay, we need to find the orbital size of the this new planet. Okay, this is a new planet. So we need to find orbital size of new planet. Okay, so we have given that the time period, we know that Kepler's law, as per the Kepler's law, t square is proportional to the r cube, or we can also write here r cube is equal to k times t square. So r is equal to k times t to the power 2 by 3. Okay, uh, so let us consider re. Let us consider re as a radius of the earth. So this will be is equal to time period of the earth, k times time to the period of the earth to the power 3. Now let radius of the new planet rp is equal to k times time period of the new planet. So time period of the new planet is t by 2 only. So whatever time is taken by the earth is half, because it is twice as much as fast as earth. So we can keep here writing like this, t by 2 to the power 2 by 3. Now if I will find the ratio, so I will get rp by re is equal to t e to the by 2 into te to the power 2 by 3. So from here rp is equal to 1 by 4 to the power 1 by 3 times the radius of the earth. So this is approximately 0.67 times the radius of the earth. So this is the radius of the new planet. Okay, now in the question given, Io, one of the satellite of the Jupiter, has an orbital period of 1.769 days, and the radius of the orbit is 4.22 into 10 power 8, so that the mass of Jupiter is about 1000th time that of the Sun. So we need to find this. Okay, so let us consider there is a Jupiter. This is a Jupiter, and this is the satellite Okay, and the distance they have given IO, consider. Okay, now due to the attraction of the Jupiter, it revolves around the Jupiter. So we can write here m, that is mass of the satellite, omega square. Why? Because it is doing a circular motion, so omega square into r, that is, we can write here m omega square into r, and this will be equal to, or the responsible force which is required this motion, or which does this motion, is equal to g into mass of the Jupiter into a small mass of the satellite by r, r square, and this is equal to m omega square into r. So if we cut out, cancel out, so what we will get? We will get the mass of the Jupiter, mj, this is equal to 4 pi square into r cube by time period of the satellite whole square into g. Why I have written 4 pi square? Because see here, omega is equal to 2 pi by t. So in place of omega, I have put this as a 2 pi by t. So we have got this. Okay. Now it is time to find the mass of the sun in terms of in mass of the sun. So that the mass of the Jupiter is about 1000 times of the sun. So can we do same for the sun? Because if there is a sun and there is a earth, so the distance between sun and earth is, let us suppose, re, and the distance between Jupiter and the Saturn is io. So can we put this equation similarly? 4 pi square into r cube means what? Radius of the earth ka whole cube, and here a radius of the io is whole cube, divided by time period of the earth whole square into g. Okay, now if we divide both the equations, so mass of the Jupiter divided by mass of the Saturn, so this will be equal to 4 pi 4 pi 4 pi square, 4 pi square got cancel out, so we will get r io whole cube divided by re whole cube into time period of the earth is above, and time period of the satellite is like this. Now we need to put the value of both so that we will get the result. So we know that radius, they have given that the Saturn radius, or the orbit of the Saturn, as a 4.22 into 10 power 8. So 4.22 into 10 power 8 divided by re. So r is, that is your radius of the earth. So radius of earth is equal to 1 astronomical unit, that is equal to 1.5 into 10 power 11, and this whole cube into time period of earth is 365 divided by time period of the new orbit is satellite is how much? 1.769 to the power whole square. So finally, if we see that mass of the Jupiter, so this will be equal to 1 by 1045 times mass of the sun when we evaluate this. So I hope you have understood this question. So thank you.